Welcome back to AP Statistics. This is Dr. Kling. Today's topic is multiple regression, which technically isn't in AP Statistics, but I think it will help you understand some of the information that comes out in a regression printout, sort of where it comes from. So in that sense, I think it'll help with AP Statistics. Okay, so let's do an example. I think I've talked before about a case where our y variable is the proportion of fourth graders in a school district who pass a math proficiency exam. It's not important that you know what that is, but just to illustrate. And we said that we're interested in, I'll call this variable x1, you'll see why in a minute, and the variable is expenditures per pupil. And that varies across school districts, and what we're really interested in seeing is, do higher expenditures per pupil, do they lead to a higher proportion of students passing the proficiency exam? So that's the variable that we're interested in. But we know there's another variable that's lurking in the background, and we'll talk about lurking variables later in this course. And that is the poverty rate in the district. So if we have a high poverty rate, and that's really what's causing a low proportion to pass, and the high poverty rate is also what's associated with lower expenditures per pupil, then we may get confused about the relationship of expenditures per pupil to the math proficiency exam. So the poverty rate is a variable that we want to control for. We want to control for it. And one measure of the poverty rate that I talked about is the percentage of students on free and reduced meals. Free and reduced meals. So the percent farms. That's actually an acronym in this education world. So we can think of this as setting up we want to have an equation y hat, that's the predicted proportion of fourth graders who pass the exam, is equal to some constant term plus the thing we're interested in, the coefficient on expenditures per pupil, I'll call that B1, plus B2 times X2. So we try to we're focused on the relationship of expenditures per pupil to proficiency in the math exam, but we're controlling for the poverty rate. So we are focused on this variable, we're going to control for this variable. That's sort of the traditional view of multiple regression. I think multiple regression has its problems, and I'll explain that again later in the course when we talk about experimental methods in general. But that was the idea of multiple regression, and what that leads to is sort of a multi-dimensional regression line. You see, you've got two coefficients. We could have other variables in here that we might want to control for. So we have a sort of a multi-dimensional regression line. We still have residuals relative to that multi-dimensional regression line, and so we still have a residual for each data point. Residual is equal to EI, and we have the sum of squared residuals. And if we take the sum of squared residuals divided by the sum of the yi squared, that's a measure of sort of, okay, the most that the sum of squared residuals could be would be the sum of the squareds for the actual yi's, or actually the variance of y. Let me do s squared y. In fact, let me do it this way. Let me call it s squared e for sum of squared residuals over s squared y. The most that could be is 1, and the least that could be is 0. If we take 1 minus that, so 1 minus s squared e over s squared y, we call that r squared. That's the proportion of variance that's accounted for by the line. So r squared is proportion of the variance in y that's accounted for by the regression variables. So when it's high, when r squared is high, meaning close to 1, we have a good fit. Low, close to 0, is a bad fit. And there's something that I call the Pythagorean relationship. That is, we have the sum, or no, let's just do s squared y is equal to s squared y hat plus s squared e. And I think of that as Pythagorean because you could put se here, s of y hat here, s of y here, and you would have that relationship. And this ties closely to r squared because if we divide both sides of this equation by s squared y, so if we divide by s squared y, we get 1 is equal to s squared y hat over s squared y plus s squared e over s squared y, or 1 is equal to r squared plus s squared e over s squared y. So those Pythagorean relationships hold for no matter how many variables we have on the right-hand side of the equation. So we could have, no matter how many variables, we have that relationship. When we only have one variable, then all of this stuff becomes sort of superfluous, but we still talk about it. So when we have our simple model, this is simple regression with just one variable, then it turns out that r squared is equal to the correlation coefficient squared. That's not true in multiple regression. You can't do something like that, but in simple regression that's true. So in simple regression, all this stuff is in some sense unnecessary, but we still learn it, and you still need to be able to sort of find your way around a regression printout and interpret all these things. So that's what we're going to talk about next time.